Okay, in the last video, I introduced the concept of a neutralization reaction and went through the basics of how those reactions work. And what I want to do in this video, which is part of a pretty large playlist extending back into acids and bases and even into molarity of solutions. But what I want to do in this video is practice writing neutralization equations so that the viewer can get a solid sense of how these work beyond the realm of just hydrochloric acid and sodium hydroxide. So for an example, what I want to look at first here would be the reaction between say nitric acid and potassium hydroxide. All right, so nitric acid is one of your six strong acids, and potassium hydroxide is one of the 5 strong bases. And again, the major products of the reaction are going to be water and in this case a neutral salt. Notice that by contrast to the reaction between hydrochloric acid and sodium hydroxide, the neutral salt we're going to get is different than sodium chloride. In this case, we're getting potassium nitrate as the neutral salt. Now, if we were to write the net ionic equation for this, it's important to recognize that in each of these cases, except for water, we have compounds, ionic compounds essentially. Well, ionic in the KOH, and ionic in the potassium nitrate, and the nitric acid is actually a covalent bond, but it's a strong acid, and you need to remember that in aqueous solutions is fully ionized. So we can write it this way as H plus NO3 minus plus K plus OH minus, and then we don't split apart the water because it's not an ionic compound. It's covalent bonds between the hydrogens and the oxygen, and then we have an ionic compound that's fully soluble, so it's going to be once again K plus and then NO3 minus. And if you look closely at both sides of the equation, you can see we have spectator ions. The nitrate cancels with the nitrate, and the potassium ion cancels with potassium ion, and we're left with hydrogen ion plus hydroxide, which produces water. So again, to remind the viewer, in a neutralization reaction between a strong acid and a strong base, this is special to a strong acid and a strong base neutralization. The predominant product is water, which has a pH of 7. And we're producing a neutral salt that has no effect on pH or on acidity. Okay, neutral salt. Now, let's look at another example. Let's look at the reaction between perchloric acid, and just to mix this up a little bit, let's take a look at one of our other strong bases. In this case, calcium hydroxide. And again, we're going to be producing water as one of the major products, and a neutral salt, which in this case is going to be calcium perchlorate. Now, we're not done with this formula yet. I want to remind the viewer that calcium is out of group 2, so its net charge is +2. So we need a parenthesis here, and we're going to require 2 perchlorates. So this, in order to balance this equation, and this is the reason that I picked on calcium hydroxide, was to make the point that for some of the strong bases, the ones out of group 2, that would be calcium hydroxide, strontium hydroxide, and barium hydroxide, that you've got a stoichiometry that's not 1-to-1 because there's 2 hydroxides here. So we're going to need a 2 in front of the perchloric acid. And now the equation is balanced because we've got 2 hydrogens here, and oh, actually we're going to need a 2 in front of the H2O. All right, now the equation is properly balanced. So we've got 2 hydrogens here, a total of 2 here for a grand total on the left side of 4. Now on this side we have a 2 multiplying the H2O, so that there's 4 hydrogens on this side and 2 oxygens, and then we need 2 perchlorate molecules, and we've got the 2 right here. So the equation is properly balanced. Now, to do the net ionic equation, let's go ahead and write that. We're going to have 2 H pluses plus 2 ClO4 minuses plus Ca plus 2. Theoretically, the calcium hydroxide is soluble in water, although I would argue to you that it's actually partially soluble. But to stay consistent with the textbooks, we'll write it this way. Whoops. I don't need this. Let me just quickly fix this. All right, so it's going to be 2 OH minus, and then we're going to produce 2 H2Os. The H2O stays together because it's not ionic. It's not a strong acid. All right, and then on this side we'll have the Ca plus 2 perchlorates, written this way. Now, again, when you look and you compare notes on both sides of the arrow, the reaction arrow, we see that we've got the perchlorates are canceling, and the calcium ion is canceling, and we're left with 2 H pluses plus 2 OH minuses to produce 2 H2O. Now check this out. We've got a 2, a 2, and a 2, and we want our coefficients to be in the lowest whole number ratio, so we can cancel the 2's. And lo and behold, the net ionic equation for the strong acid, strong base neutralization using a group 2 hydroxide, so calcium hydroxide, strontium hydroxide, or barium hydroxide, where the stoichiometry is not 1-to-1, right? We've got 2 to 1 to 2 to 1. All right? Now, nevertheless, utilizing these strong bases, you see that the final net ionic equation is the same as it is for a group 1 hydroxide. So this is unique to the strong acid, strong base titrations. In every case, the net ionic equation is the formation of water. The key thing to remember is that the pH of the final solution is going to be 7. And with that, I'm going to go ahead and close this video.